Applied Houdini is back with a whole new series on particles, starting with this one, Particles I Fundamentals. We're going to talk about what makes a particle, how does it move, what affects how it looks, and what are our production ways of setting up a simulation, of how to bring particles into a simulation, and even how to make huge changes that affect the look after the simulation. We're going to talk about key attributes, key workflows for getting what we want quickly, and you'll see in no time at all, we're going to be able to build up this really cool magic effect that you can see here in the video. So without wasting too much more time, let's get started. All right, well, before we actually get started with our magical effect, let's just spend a little time in this quick demo scene I set up to show you the basics of what particles are and how they work. Before we recombine lots of millions of particles into one effect, let's just start with one particle. So what is a particle? A particle is a point essentially that moves through space. It remembers its position, and it has a velocity, which is pointing it in some direction. So that is at its core really all particle simulation is. You could write a perfectly decent particle simulation with just those two pieces of data. So in our case, here's our particle represented by this big old sphere, although the size of it really doesn't matter. It starts here at 0, 0, 0. 0 in the x dimension, 0 in the y dimension, and then 0 in the z dimension. Now we're only looking at the x, y here for simplicity, but you know, there is a z dimension too, because of course this is 3D. So it has a position, and that position will be modified every frame by our pop solver here, particle operator solver, and it's going to update the position based on the velocity. Now, in this demo, I've decided to start this off with a fixed velocity of 3, 1, 0. Again, don't worry about the nodes themselves yet. We're going to get very much into each of these nodes and what they do, but just be satisfied for now that this particle, as you can see here, has a velocity of 3, 1, and 0. So what that means is it's a direction that the point is moving in over time. It's not a position, which is just where it is. The velocity is essentially the difference between positions, like so. The only reason why it's able to get, like if we have a position of our point here, and we have a position of our point over here, if we were to subtract those two positions, we would have an arrow that pointed from 0 to here. And you can kind of see that arrow represented as this green line also here in Houdini. That shows us the velocity. And the velocity is not changing over time. In fact, the velocity is staying the same as the point changes. The velocity is saying, go this far every second. Now, a second in Houdini is 24 frames. So in theory, if it starts at 0, 0, 0, and there are 24 frames in a second, by going here, it should have reached this distance. And sure enough, it does. 3, 1, 0, 3, 1, 0. So see the numbers here on the x-axis, 0, 1, 2, 3. You can see it moving for every 3 across it's going up 1. And that is, of course, because 3, 1, 0. So I hope I'm not beating that to death, but that is essentially all a particle system is a point and a velocity, and we're going to modify the velocity in a variety of ways. So what's one way we can modify that velocity? Well, really the main way is never really to modify the velocity directly itself, but we apply forces. Much like we've applied forces in our volumes lessons and in our rigids lessons, we can apply forces here as well. So this is going to apply a force in the negative y direction. So if this is the y-axis, the negative y points down, and you can see that exemplified here with these red lines. And that's because this is red, as you can see. So we have this force attribute here, and these attributes are pieces of data that are stored on every single point. Now we only have one point right now, so we just have this 0 here, point 0, which of course is the first point. Once we have 4 million points later being added into the sim every single frame, or every second actually, we'll have a huge spreadsheet of all of this data. But again, let's just stick to one for now. So we've got this force here. And if I press play now the point is curving, like so. So what's happening frame by frame? We're still starting with the velocity of 310, starting at frame 000. But as we move forward, this force, which is being applied at every frame, is pulling the overall velocity down. See how it started? The y started at 1. So this negative force is pulling it down. So every frame, the velocity, the actual direction and speed that it's going in, is being pulled down further and further. Like so. Because that force is being applied at every frame. If I were to turn that force off, let's say here, I'm going to say after this, no more force. And you can see the force is now turned off here. It's going to curve at the first and then just keep going straight after that. Because notice how the velocity was being modified by the force for all the frames that it was allowed to. Then after that, the velocity stays the same because the force is no longer being applied. Now it still has this new velocity based on where it started with, and now it's just going to keep drifting off in that direction. So this force, and I'm going to go back to making it always apply, this force is a force that you might be familiar with. What is a downward force? Well, it's gravity. In fact, if you do negative 9.8, that essentially is our gravity force. And you can see it starts by going up, and then it just kind of plops down. So that's one kind of force. Another force would be, let's say, if it blew back this direction. So you can see it's the same idea. This force is being acted on the x-axis, so it's modifying the x. We could have two forces on at the same time. Now we're not going to get two different force vectors. What we're going to have is these two forces added together. So here it is, 0, negative 1, 0, and this was negative 2, 0, 0. So the total force is negative 2, negative 1, 0. Again, it's just this one added to this one. And you can see them both being displayed in the viewport here. So now if I play it, I get this kind of, it's going this way because of the initial velocity, but it's being pulled down by one force, and it's being pulled back by another force. Both of these forces together are giving rise to more complicated behavior. So those are pretty boring forces. What if we turned on this force? Look at that, wild. This force is using a noise, and noise comes up a lot in dealing with particle behavior. This is going to apply different forces in different directions and over time even. So watch what happens when we play this one. The behavior of the sphere is going up, it's curling around, it's coming back down. And that's because all these force vectors here are changing over time. Look at it here in the spreadsheet. We're still starting with the same values here. We're getting this crazy force vector here, and it's changing over time. Kind of smoothly and in a kind of windy manner. It's not totally random, but different enough that we didn't specifically set out to say, oh, I know exactly the way I want this particle to move. We are simply saying, well, I have a force here and I want the size of the, let's say the wind gust to be approximately 30 units. I could make it smaller and you can see how it changes in here, and who knows what we'll get from that. So I'll change it up. So we're basically giving it rules, and that's what a lot of particle simulation is coming up with rules to apply to millions of things, and then that'll give rise to interesting behaviors. Could turn these guys back on too if we wanted. Who knows? So these two are constant still, but this one's moving around a lot, and so on and so forth. So that's I think a good quick primer in how particles are working. To recap real quick, we've got a point has a position that it knows about every frame. It has a whole bunch of forces that are being applied to it that are modifying the velocity. And ultimately it's the velocity which is used to update the point. And as a quick little technical note, if you recall, the velocity is how far it moves per second. That's how far it moves every 24 seconds, or rather 24 frames. Of course, we're seeing an updated position every frame. We don't wait for 24 frames before we move it from here all of a sudden to here. Ultimately, what we're seeing is 1/24th of this movement every frame, which of course is why we get a little piecemeal movement. And while that velocity vector is being changed, we are getting a whole new velocity every time, but ultimately we're only actually applying 1/24th of that value every full frame. Later on, we can ask for it to actually calculate more substeps per frame, or less, or whatever. We can go crazy with that stuff later on. But it should be enough to realize that the velocity is saying the direction it's moving in, and really how far it's moving by how large these numbers are. If I were to change this velocity from being 310 to double that, 620, it's still going to go the same direction. It's just going to go twice as fast now. Note that even though 24 frames is still 1 second, it actually took a half second to reach this area now. Whereas when it was like this, it takes the full 24 frames to reach that area. So a velocity, in essence, is a direction, and also how long this vector is the speed of our particle. So before we finish up, some other interesting little attributes that we'll go into more in a moment. You might have seen this age one hanging out here. That's simply storing when the particle, how long it's been since the particle was born. So by 24, it's been alive for 1 second, half second, 12, and so on. And we have a whole bunch of other little ones in here. We have ID, which is a unique number that identifies this particle. Even if it dies, a new particle will never get that number 0. And some other attributes that we will get into very soon. But these are the main ones. Great. We've made it through the absolute basics of particles. All right, with the particle basics out of the way, let's get started. So let's make a new project. Call it something like particles. Maybe particles 1. Yeah, that's good. So that's nice. By having that, now all of our stuff will be saved in one area. So I could say go to job, which has been set to that thing that we just made. And I like to just put them right here in the job area, and I'll just say particles.0.hip. And you'll see if we check it up here in the edit aliases and variables area, that you'll see under variables, the job is set to that thing we just set up. So we'll have it's already all nice and organized and set up, and we won't be butting up against any other project files you may have. Great. So that's that. Let's also set up our viewports in a cool way. I like to take the scene view here, go up to this upper right-hand corner here, and say split top and bottom, like so. And we'll go to the plus sign here and say new pad type, pane type rather, geometry spreadsheet, and close that LC view. This will show us all of our attributes and simulation data, and we're definitely going to need that. So you can click this down arrow here for now to minimize it, and whenever we need it back, we'll just click the up arrow again. What else we want to do? I want to make this a little bit wider, and instead of splitting it up and top and bottom, let's split this left and right, like so. And I'm going to say this will be associated with this one. They're both 1 here. This will be associated with this one. So I'll be able to look at my nodes in here and look at their parameters up here. And we'll have this be 1 here. So we can maybe change simulation settings over here, have the actual simulation running here, and just see the results of that without having to keep navigating around. You'll see what I mean. In the meantime, go up here and let's just save it. Save current desktop as particles, like that. So now we can get back to it whenever we want by coming up here. Great. Save it again. All right, so let's get started with our actual simulation. So first things first, over in the object area here, we'll press Tab, start typing out geometry to drop down a geometry node. This is actually going to contain our emitter and also our simulation for that matter. And I'm just going to type particles like that. And I'm going to dive in by double clicking, select this file SOP, delete it because we're not going to be loading any geometry from the disk. Instead, we're going to press Tab and type out pig. And let's just use this test geometry pig head thing that I like to use in all my other lessons. And if you haven't seen my other lessons, check them out. Otherwise, welcome. Welcome back, I should say. So just move our camera so that we're kind of looking at the pig, kind of like this, kind of in the center. And then once you find something nice, control click on the camera. And this is going to be the actual rendered area, this light stuff, not this dark stuff out here. If you missed it, click the lock while we're in the camera and we can move the camera around. You can see it's changing the values up there. But just something like this should be fine. Eventually we're going to have particles kind of whipping out of here, going every which way. And we just want to make sure that we have some extra space to capture that. So turn that lock off when you're done. That way we can move the camera around and pop out without moving it. I would say just go ahead and save it. Why not? And we are on our way there. All right, so with that all done, let's jump back into our particles area here. I'm actually going to turn off this grid thing. You can see that there in the viewport. We don't really need that. So this is a SOP. All of these things that modify geometry, these are all SOPs. So we have a pig head here. We could put a transform down here. You know, it might rotate the thing, or maybe we'll select some points and press T to like move them around. Either way, this is all nodes that are surface operators because they're working on the geometry, or really the surface of the pig. Now what we actually are going to end up doing is go into the DOPS area, the dynamics operator area. So let's drop down a null here. So we'll say something like, this is the emitter. This null itself doesn't do anything. It just sits here and says, I am something that can be pointed to by something else. You'll see what I mean later. But for now, just put that there. It mostly just makes our setup cleaner and more easily labeled and easy to follow along. So we have that. So like I said, we have these other op types. What we want to type here now is actually pop network. You can see it there. Drop it down. If SOP meant service operator, POP means particle operator. Of course, that's what we're doing this lesson, is particle operations. Truth be told, though, real POP nodes aren't really used anymore. They've been rolled into this DOP thing. Don't worry about this terminology kind of stuff right now, but just so you know, when we're in our networks and whatnot, and we're seeing like, oh, POPs, why are they called POPs and nothing else? That's why, because there used to be particle operators, but now they're all just in the standard dynamics operator area. So you probably noticed that we got these squares. These are already particles that just got spawned, but they're showing up black because this pig head has a material on it, the skin color. It's not playing nicely with the particles. We'll make our own colors later. So for now, let's just delete the material off of it. You can see if I middle click and hold, it's called shop, meaning shader operator material path. Let's just get rid of that. So choose it from here, it's gone. Now it has no material, and now you'll see in the particles, those squares go away. Great. So now let's finally take a look at what's going on. This is the simulation area itself. In fact, I'm going to make this a little bit bigger, like that. We're not really even using this side too much yet. So what do we see here? Well, we have the output. That's self-explanatory. This is the end of our simulation. So everything that feeds into it is the sim. So working our way up, this node is the solver itself. Solving in dynamics means evolving the state of the simulation forward by, let's say, one frame or one time step. So when we had our particles moving across the screen before, the solver is the thing that's moving everything to the new location. So this is kind of the brain, as you can see. There's a brain, and it's thinking about particles flying around it. It's the thing that's actually doing the calculations of moving the particles forward. We won't need to change too much, if anything, on this at all this entire lesson. So let's just keep it as it is. The pop object is the particle bucket, so to speak. It is the container that's going to store all of the points that we're putting into it. Again, that's something that we can really go into more depth in later lessons. We probably won't need to change anything on here either, which makes our job nice and simple this time. But stuff like how much it bounces, how much friction it has if it's colliding against a surface, temperature if that becomes relevant for whatever reason for you, all that stuff will be set on here. What we're mostly going to focus on this lesson is this branch, which feeds into the pop solver here. You can see it says on the bottom, sources, post-solve, we've got pre-solve. These are basically just things that you want the solver to do. So the main one that we have here right now is a source, a pop source, meaning simply a particle source. Without it, we have nothing. We press play, the sim is running, we can see the cache, represented by this blue down here, is filling up, but there's nothing to do. There's no particles in here in the bucket, it's empty. The solver is evolving and nothing, and then outputting nothing. So the source is really where we're going to start to bring particles in. So the blue represents the pig head, which is because we have the guide here. Turn the guide on and off to make the source, that visual go away. It'll do the same thing either way. And what is it doing right now? Well, it's randomly spawning particles all over the pig head. And if I move my mouse around, you can see, sure enough, we can basically see the pig head. All the particles they're not spawning inside of it, just along the surface. And every frame, more are being added. So that's our simulation. They don't have any velocity. They don't have anywhere to move. Nothing is telling it to move anywhere. So they're just all hanging around where they first showed up. Now, how does it even know to bring in particles on the pig? Well, that's simply because the geometry source says use first context geometry. What does that mean? First context? First context simply means this input 1. If I let's say I got rid of these and I said, put it into here. Well, now nothing happens because there's nothing here. There's nothing in the first context. I could change the third context though, and there it is. So that's what's happening. We could also manually point to it in the SOP, which is often what you'll end up doing actually, where we say point directly to the emitter, which is that so-called signpost, which is again this node here. So now this connection really doesn't mean anything. It's just pointing directly to that. So that's what's so wonderful about Houdini is there's so many ways we can do things. So we'll just leave it like that. That's fine. That's probably the most robust way. So there they are. So the emission type is scatter them onto the surface. Now we literally have a node called scatter. And if you hook it up to geometry, you can see it does that. It'll scatter as many points onto the surface as you like, or at least as much as your computer can handle. And that is what the pop source is going to do within the simulation every frame. So we can also refine it to maybe an area that is in a collection of polygons, maybe only source them on his ears. We have the emission attribute where if maybe we will set an attribute, and spoiler alert, we're going to say only spawn particles in certain areas that are defined by some value. That's all well and good. Probably one of the ones we're more interested right now is how many should even come in. Impulse activation, which is on because it's set to 1, means spawn this many particles every frame. So once again, 0. But if I were to say spawn 10 particles every frame, you can see by middle clicking and holding on any of these nodes, you can see how many particles there are. Pop object, remember that's the bucket, that's this thing here. So the pop object contains 400 points. And these are some of the attributes that we looked at in the first chapter. Things like velocity and the position and the age and all that stuff. That's all being stored in here. So anyway, 400 points. On frame 1, there's 10 points, because that's what this is. On frame 2, 20 points, and so on. So this is literally saying do this many every time this node is evaluated. And right now it's being evaluated 1 time per frame. Fans of this lesson series will also hear a siren outside my window right now. That seems to happen a lot in this neighborhood. Broadcasting live from downtown San Francisco. Anyway, so we're not going to use the impulse one. Instead, we're going to use the constant activation, which means basically spawn this many particles per second. There we go. So it's not spawning 4,000 particles on the first frame, but these will add up within 24 frames to be about 4,000. You can see it kind of missed it by a little bit, but essentially is that. We can say how long we want the particles to live, and we can say maybe start them in different locations. By changing the seed, you can see the random distribution will be different. We don't have any particular preference for this. We'll keep that at 0. And I'm going to say the life expectancy is how many, again, seconds, not frames, that we want these particles to live. So I'm going to say if I want this to live for 1 second, or even let's say a half second, that'll probably be easier to see. These will only live 12 frames. So you can see it's never really getting out of hand. It's spawning new particles and all particles are being killed. Spawning new particles, all particles being killed. When this was originally this much, the 100 seconds, it just keeps going. And in fact, I don't even want to have our simulation be 240 frames. Let's click this guy here, change it to 120, like so, apply it. So now we have 120 frames, which will be about 5 seconds. In fact, it'll be exactly 5 seconds. Great. So we got that. Well, we can come back and change a lot of stuff later, but I'm going to say the life expectancy, again, I want them to, because this is an energy effect, I want these points to fly out, like flare up, and then disappear pretty quickly, if you imagine the way like sparks would. So I'm going to say life expectancy is 1, and the life variance is also 1, meaning the baseline life for each particle will be 1 second, but it can be plus or minus 1 second also. So each particle will have different amounts of time it can stay alive for. It can basically be 1 plus or minus 1, which means 0 to 2. Because 1 minus 1 is 0, and 1 plus 1 is 2. So some of these particles will stay alive for 2 seconds, some of these particles will stay alive for 1 second, and everywhere in between. If we want to see what those values actually are being initialized to, it's time to bring up our geometry spreadsheet from down here. Remember we set that up before? And if you didn't, add a geometry spreadsheet down here now, or I guess just use the one that's up here. But I prefer to be able to see it. So when we bring that up, this is our simulation. So that's the pop net, meaning that's the node that we're in. Here's the pop object. Remember, that's the bucket that we're storing the particles in. Expand that out 1 time and choose geometry. Again, if we middle click, you can see geometry is the subdata that stores everything in it. And here it is. Look at all those cool attributes. There's only one attribute I'm interested in right now, and that's called life. Life is how many seconds the particles are allowed to live for. Now remember, we predicted that it would go from 0 to 2 because this is 1 plus or minus 1, and that's what we have. It's not going to be exactly 2, but it's pretty close. And it's not going to be exactly 0, but it's pretty close. Obviously, if we had no variance, it would all be 1. And as we increase the variance, they can diverge more and more. Obviously, completely an artistic choice, but I think this will be nice. From 0 to 2, we have another attribute called age. Age is how long it has been alive. It's not a percentage of the of how long it's allowed to live. It is only a recording of how long it has been alive. Once it gets to this value, so like particle 33 here is about to die because it's about to exceed its life and it will go away. So something like that. Cool. When it reaches the end of its lifespan, there's actually another particle called dead. Well, they're not being set right now. They're probably just being culled immediately. You can set the dead attribute yourself if you want these particles to die prematurely. For example, we can just put in a pop wrangler, one of the many nodes that is just under this pop menu. As you can see, it's pop wrangler here. This allows you to type just a little bit of script yourself if you want. I'm going to use the @ sign, which is how you read and set attributes. I'm going to say dead equals 1 with a semicolon at the end. That's going to kill everything. The solver knows to kill everything that has dead equals 1. In fact, that's under update here, reap particles. And you can see all particles with the dead attribute set to 1 will be deleted. So don't take my word for it. Just listen to the pop solver. That's one of many particle attributes that we can modify and have a good time with. I'm going to turn that off for now, though. We don't need that yet, and we may never need it again for this lesson. But that's a particularly important attribute to modify later. So, what else we got going on here? Let's come back in here. We have attributes. We can inherit all the attributes from the surface that we are spawning from. So this surface back here. So anything that we set on here can be inherited, and we're definitely going to want to do that, by our particles. That could be things like velocity or color or any kind of other arbitrary data that might be important to us. For now, there aren't anything specifically we want to do, but we could do this. We can say set initial velocity. So much like our life variance being plus or minus 1 on this, the variance on our velocity will be plus or minus 1 on these velocity vectors. So if they're 0, it'll still be getting no velocity. But finally, what happens if I say 1, 1, 1, the particles move. This velocity is being set only on the frame that the particle comes into being, meaning the frame that it was birthed. You'll see a reference to that under the birth tab. We can make a group of them, and we can set these attributes like the life. Much like the life being set on their first frame, this is the velocity being set on their first frame. We can put these little streamers on, and you can see them fly. Whee! Like so. Like little tadpoles in a pond or something. Pretty cool. That doesn't affect when they die. You can see them winking out of existence as they get too far. It's not the distance that they've gone is too far. It's simply that their age has reached their life attribute and they've been reaped. Cool. So we can do that, but this is just a noise. This is a purely random velocity that's being applied, and it doesn't look very interesting. So let's come up with a more interesting way to apply a velocity to this. All right, so let's turn off this. Let's go back to use inherited velocity. So it's back to inheriting, well, nothing. So I want to show you how it can inherit things. For example, I can say, let's say if I drop down a color SOP, I'm going to make the color of this be, well, I could make it just red. Let's make it more interesting. I'm going to say just be a ramp from attribute. And the attribute can be P. Cool. So now it just has some colors. That's really the whole point of this. So it's got some cool colors. And now if we come back in here, note that the particles themselves have cool colors. They have an attribute called CD, which means color diffuse. Back in here, middle click and hold, this thing here made a CD attribute. It didn't exist here, it just had position before. Now it has a position and color diffuse stored on every point. We can see that attribute like we can see any attribute just by looking in here, red, green, blue, all kinds of crazy colors. The colors, actually, as a point of fact, are based off of the positions they are in world space. It just happens that that looks like a rainbow. But it's perfect for this demo. So coming back to here, if I were to say set initial velocity, they're flying away and they retain their color. The color is not being updated or anything every frame. It was stored on that first frame when it was inherited, and now it just is that color. Awesome. So we don't need to inherit the color in this case, but what we really need to inherit finally is the velocity. That's how we're going to sculpt our simulation, is by predetermining what the velocities should be. So as an example of setting velocity, I'm going to use a transform here. Again, it's before this emitter SOP, so it'll still be reading. This is still going to be the source for the particle. So we can do anything we want before that, and it's automatically going to feed in. So I'm going to say on this transform, Alt and left click on the attributes we want. Not sure where that's. Okay, weird. So Alt left click on that and that. And then I'm going to go to some other frame, like 8. I'm going to rotate it. And I'm going to move it. I'm going to Alt left click on both of these again. So now we have a keyed animation from here to here. And I'm just going to move it a little bit more. Alt left click there. And I think you can do this as much as you want. But the point is that we're moving it around. So it inherently has a velocity now. Each point has a velocity that gets itself to its new position. And that's all well and good. If you remember though, those velocities are stored as v. So when particles come out of here, we have a v attribute. But if we want to inherit the velocity, that means we have to have a v attribute here, which we don't. Even though it's moving, it's not actually being stored as a velocity attribute. So one of the weirder places that you can do this easily is the trail SOP. The trail SOP is usually used for making copies of your geometry as it moves through the space, but you can actually just have a compute velocity also, where it's just going to do the difference of the current frame to the previous frame, and it's going to store it. And we can see that with our velocity trails thing. So you can see here that streaking is the velocity, like that. So now we have a v vector. And that means if we come into our sim, you can already see it. It's inheriting, well, actually, let me go back to use inherited velocity. It's going to inherit those velocities. See that? In fact, for this, I'm going to turn the guide back on. You can see they are moving. Well, the first ones don't move because on the first frame there is no velocity, but you get the idea. They're inheriting essentially the inertia of the pig moving. If you really want to see it go wild, we can just up the amount of particles up. So now we don't have like a random spray. Now we have like a spray with some form to it. It's based on the movement of the underlying object. They all have their own velocity vectors, and you can really see how that is working. Now we can add on random movement on top of that, which is why we have add to inherent velocity, where now we can add this 111 jittering on top. So it's still largely going the same way, but it's also getting some randomness on top of it. Obviously you can adjust this. You can just give it a little bit of random on top of it, and so on. Although once again, let's just go back to using the inherited velocity. Great. So we've inherited color, we've inherited velocity. We know how to change the life, how many are being made. We are well on our way. All right, so we learned how to make velocity by actually moving this thing around and then calculating a velocity from that. We also set our color manually over here and also inherited those colors as well. But delete all that. Let's calculate some interesting velocities and colors and emission attributes and all kinds of stuff procedurally using the handy dandy point Vaught. The point Vaught, meaning vector expression language operator, will allow us to write a little tiny program to do exactly what we want to do rather than rely on nodes as they already exist. So I'm just going to say emission, velocity, and color. So there's nothing really on the node itself of particular interest to us. We're going to want to dive into this and build a little program in here from little building blocks. So, for example, I want the velocity to not be just randomly thrown out of here, and I don't want it to be based off of how it's moving. I want it to be stock still, but I want the particles to fly out using the normals. I want them to fly out in the direction that the surface is facing. So to see that, I'm going to drop down a normal stop here, and it's going to make, let's say add normals to the points themselves, and this little visualizer here, display normals, click that, and there we can see these vectors, these lines, are pointing away from the surface. I want my particles to move in that direction. So for example, if I fly into here, I can say, well, we just made an n attribute for normal, and there it is. This is one of the commonly used attributes that they just have on this. We can bring in any attribute we want, but these are commonly used ones. So I'm going to say take my n, and you are now being copied into the v. V, as we now know, is for velocity. And if we visualize that, the n vector is literally pointing this way, and it has the line point that way. For velocity vectors, they actually point the opposite direction because they're meant to be a tail that is following behind. So even though they're the exact same vector, they actually point in opposite directions. So sometimes I like to use the normal one because it's actually pointing out where I can see it rather than inside where I can't. Anyway, we've set the v now. We have it. V has been copied from n. And if we look at this, sure enough, they will be moving away from the surface of the pig. So that's cool. So how about we limit where the particles show up? Right now they're showing up everywhere, all over the surface. So we can do that too. I'm going to say, let's make a color on the surface that will signify where the particles should be. So I'm going to make white patches where we want lots of points, black patches where we don't want any points. There's lots of different patterns to choose from, all here under the patterns menu. The one that we want is actually under the noise patterns over here, which is called anti-aliased flow noise. We could use periodic noise, turbulent noise. A lot of these noises are cool. In fact, many times I do use turbulent noise. This time I'm going to use anti-aliased flow noise. So the anti-aliased flow noise is a time and position dependent noise. If we limit it to just position for now, as an example, where every single one of these points on this mesh is going to run through this program and have some value come out the other side. So for example, every point has a position, as we well know now is attribute P. That is the input to this little machine here that makes a noise pattern, meaning a white to black, a grayscale pattern of noise. If I offset the noise, you can see it move around inside of the thing here. I'm going to go back to 0 though. So that input position, output this color here. It's not dependent on time right now. It is only dependent on the position. But nonetheless, we created a CD attribute. We can now use that CD attribute back here on the emitter. You remember I kind of skated over this before, but on the source tab, we have emission attribute. Set it to the color, like so, and now we can see they're only being emitted in certain areas. Kind of hard to see. So I'm going to say, there we go. With this being displayed and this just selected, selecting it is enough to have the points show up. So we can see the points are coming from these white areas. What are the actual values for this? We'll select this guy, open the geometry spreadsheet, and take a look. Here's the color attributes. The colors are going from approximately 0.25 to 0.25. You'll notice that it's the same value for red, green, and blue. Now that is why it's black to white. because they all have the same value. That is because on the noise itself, it is a 1D output, meaning it is only returning one number. This dotted line here means I'm a 1D output being fed into a 3D, because color has 3 values. It allows you to do that. It's just kind of warning you that, well, technically I'm not taking a vector output and putting it to a vector input, but I know what you mean. You want whatever this value is, this one-dimensional single number, to be copied into all 3 values here. I can actually do a 3D output like this. And now we have that it's now a solid bar, and now we have 3 different numbers for red, green, and blue, and you can certainly see that on here. Some of those values are still less than 0 though, and they just look black. In our case, the emission attribute on our source thing here, a 3D vector doesn't mean anything here. It just simply wants a number more or less between 0 and 1 to say how many particles should be here. So I'm just going to say you just generate a one-dimensional noise for this. It's just more intuitive. So there you go. For values that it's negative, it just simply won't get anything. And as we were already seeing with the emission over here. Like so. Great. So that's fine. Let's have it actually make this white area move around over time though. Like I said, if we delete this, we can go back to here and get a 4D input. Note that as long as this is connected, this 3D output to the input here, we will no longer get the option for a 4D input. So watch out for that. Delete this first, then go to 4D input 1D noise. And now we can do that. But first, you'll notice the colors change to bright green because that's the connector for a 4D input. What do we mean by 4D? Well, it's the classical fourth dimension, which is time. So we take position, X, Y, and Z, and the fourth dimension, time. All 4 of those values together can be input into there. In order to do that, start typing vector and choose vector to vector 4, this one here. Put it down. It wants a regular 3D vector here, and then the 4th value will be time here. Now we have that bright green tennis ball looking thing to pump into this. And sure enough, now it changes over time. In fact, we can even control time, right? We're just reading in whatever the time is in seconds, but we have even more control than that. I can say, for example, before the time actually reaches this noise, let's change it. Let's multiply it by something so we can actually make it go faster or slower. So like I could put this here and say, we'll call it something like time scale. And then this will be like the nice pretty thing that we see up top. Tame scale, that's not right. There we go. So putting it to 1, it will be essentially what it already was, because any number times 1 is itself. But I could change it to 0.5 to make it go twice or half as fast, or even less, as you can see. Super slow. Or I could go 3 times as fast. I'm going to want it to go fast like this, because this is like a quicker, energetic look, I think. Cool. So let's see what that gets us. I'm going to go back into the little camera here. So now you can see it's being emitted from different places all over. So as things light up with that white area, particles will come out of those areas. This is a very common technique in production for getting a random looking source. If something's on fire, we want like fire to be shooting out from all over the place. If we want a magical effect like this one's going to be, we want it to just be, traveling all over the surface to make a much more interesting look than it just all flowing out from the same place at the same time. Similarly, we kind of have this big wave effect where everything is kind of going the same speed, because everything is going the same speed. It's literally all going the speed that the normal is, which is a unit vector, meaning that it is 1 unit long. Everything's going to go the same speed there. So why don't we just take this noise that we just made and multiply that by the normal. So now, if we look at this again, we went from having essentially, if I take the normal, let's say we'll put it into, we'll put it back into here. So we went from having this, these were the unit normals that we were using for the velocity. But now, if I say the normal is going to be multiplied by this white to black field here, which is going to be the velocity in a moment, you can see they're much smaller, but they're also different sizes now. Now they are the highest when they're in the midst of the white areas, as we would expect, and they're the smallest, or just pointing inwards, in the darker areas. So I'm going to delete this thing here. The important thing is that it's feeding into the velocity, because that's actually what's going to be used. So let's see what that looks like. Now, like I said, it's much slower, but now we can see the speeds vary. As that energy field travels across the surface, it's varying everywhere. So now we're not creating quite as predictable waves as we were before, especially some cool little pops and fizzes around here. So that's looking pretty cool. Whoop, there we go. All right. So that's looking pretty cool. But there's still a lot we can do though. So let's dive back into the point Vaught. And for example, right now we still have the velocity is kind of just going in the one direction. It's going out away from the surface. So what if we take this paradigm here where we're using the anti-alias flow noise and used it for the 3D noise that we talked about earlier? So looking at this here now, remember that the 3D output means that we're getting, and I'm just piping into the color for now, it means that we're getting 3 different values for the R, G, and B. And that's what we're going to want to use because, of course, our vectors that are defining the direction, pointing the direction we want the particles to go, they're gonna use an X, Y, and Z. So let's put this color back to where it was. I'm just gonna say instead, use the normal. Let's take a look at the surface here. So that looks pretty cool as it is. And as I move this around, we kind of have that wind blowing around along the surface here. It's pretty nice. What if we normalize it to ensure that we have it be a unit vector, like so. Whee! That looks cool. So let's take that value and add it to the normal vector we were already using. Bearing in mind, again, that currently the one that we're already using is everything pointing the same direction straight out. And now by adding to that original normal vector, this guy, now we'll have a mix. So let's see. Now we've kind of got this look. Kind of hard to see. Maybe it'd be better if we had the actual particles tell the tale. So I'm going to come back out here and say popnet, do your thing, and there we go. So they're no longer just pointing straight out. They are being affected by all kinds of directional changes from that. Pretty cool. So what else then? It's always what else? What other patterns and noises can we keep layering onto this? Well, I would say right now it's going kind of slow. So let's kick it up a few notches. Now I'm going to start to work over here too, where I'm going to say, I'm going to do a lot of my VOP level, my emitter level changes in this window and our solver level things over here, or our simulation, I should say. So for example, we lost a lot of the speed when we first started multiplying in this guy. So I'm going to say, to make up for it, let's make him just have a higher amplitude. So now it's pushing out that much farther. Alrighty. I'll give there's the little trails. So that looks cool. Maybe it's going too fast. Or, put another way, maybe they're just kind of uniformly just going, they're just kind of getting emitted and they just kind of keep going the same speed, which of course is exactly what's happening. So I'm going to say, let's introduce a new thing. We talked about forces already, but we haven't talked about the opposite of that, which is called drag. Pop, drag, particle drag. Drag will basically reduce the energy on the particle every frame. It's essentially kind of a force pushing back the other direction. It also could be considered air resistance, as this is putting it here. So what can be a nice effect a lot of times is having things erupt quickly and then slow down. I'm also going to take this opportunity to just have more particles come out of here. So let's just make this be that. So now we can kind of see a little easier. So that's cool. So they're slowing down. We can see them kind of slowing down as they get out farther. But it's not enough. I want them to start quickly and slow down quickly. You kind of get a much better feel of explosiveness from that. So now you can kind of see they're erupting onto the scene quickly and then coming to a stop. Of course, now they're just not going as far as I would like. That's okay, because I want to add a much more explosive force into this thing now anyway. Looking at our emission source here again, we can see that we have these general gray areas, and we know that we're multiplying our velocities by these kind of general gray areas. What if we added some spikes into it? So it's not just this kind of blah pattern. That is a pretty key concept in effects, which is layering, again, patterns and noises on top of each other to break up, and to keep breaking things up more and more and more. So I'm going to take our 1D fluid noise here, copy and paste it, and just so we can get a look at it, I'm going to say pump that into the CD for a minute. Obviously it's the same right now, but what if we up the frequency quite a bit? See how the features are getting smaller and smaller and smaller and smaller? I want these to be really tiny peaks. Of course, now at 10, it's just kind of chunky because we don't have enough resolution on the model itself. So to that end, come back out here and say, hey, how about we add a subdivide like that? Now we have all this resolution. And looking at it now, you can see we're able to capture more of that small detail. And in fact, if I go to 2, you can see it getting captured even better, because this little program here is being run on each point. So if there's not enough points to capture those small details, you're just not going to see them. All right. Now I still actually want it to emit, I want the color really to still just be that one big blah one, but I want this one to influence the velocity. So let's pump that, let's rather not add it here, let's multiply it by the vectors that are reaching into our thing here. So let's take a look at that. See these little spikes that we have now? That's again because without this, it's just this big kind of blah shape, which was interesting, but now it's even more interesting. How about that? And I can already see that the velocities have gotten even smaller. So why don't we take the amplitude and multiply it times 10? So we get to that. So let's see what that looks like. And I just promised us that I would be doing that change over here, and then it meant right back to over here again. My mistake. I'll try to be better about that. So coming back into the solver again, turn that off. Let's see what we get now. So we have those big spikes, but they're still being toned down quite a bit by the drag. That's okay. What if we turned it up even more? This could be like 30 or something. So that's looking pretty cool. Let's see. What else? Always what else? I would say one thing, actually now that we have this subdivide going on here, it could be nice to perturb the surface here with a mountain. We drop a mountain down and say like, I don't know, do like maybe 0.1. So we'll animate the time with a $T. The idea being to get this kind of like undulating, again, energy looking thing. Again, this is still going to be the source, but now we'll be sourcing it from this slightly moving around area. And we might even go higher than that. Something like that. That's cool. So that's nice. That's a quick and easy way to get something like that going. I'm going to come back in here. Let's get rid of this normal thing just so we can see again. So this is our what our emission area looks like. We could come into this thing, we could rough it up a little bit. See, the higher we make this roughness, the crazier it gets. That's obviously too much. But maybe we might move it up a little bit. Just to crunch it up, just a little. Could be nice. And I'm not even gonna like look at this one, but I'm just gonna crunch it. And maybe even crunch this one a little bit too. It just again, it just breaks it up a little bit. It doesn't add like the extreme peaks that this breakup did. But just lots of little things that add up to be a nice big thing. So there we go. So pretty satisfied with that is for now. We're going to want to actually start looking at what this appears in a render before we make too many more modifications to this. So we've toyed extensively with the emission properties of our sim. But what happens when the actual particles are in the simulation? What happens then? Well, we added the drag. We also don't need this merge, by the way. I should have gotten rid of it a while ago. And let's just get rid of this now, too. We're never going to use that. So the pop drag is, again, slowing them down. But what if we sped them up again? Let's, not as much as, we're ultimately going to lose a lot more energy from this drag. But let's make a pop force and add some arbitrary force. So they're shot out into the world. And then we want some force in the world to do something. So for example, as I showed earlier, we could just give it gravity and do that. And now they're just falling. Which is weird because there's a lot of drag preventing it from falling as fast as it should be. But nonetheless, you could do that kind of force. But I don't want to do that kind of force. I want to give it a kind of swirling in the air force. No, the air force. So that's what this noise is for. Now the amplitude is set to 0 right now, so we're not seeing anything happen. Turn the guide on if we wanted. And that will be over at the origin there in the middle, but I don't even care about that. Let's just turn the amplitude up, and let's turn up the roughness a little bit, and the turbulence itself. The turbulence is kind of getting more little details in it. In the way it moves around. So check this out. We can already start to see it. Where before, it just came out straight and slowed down. Now, with this on, they swirl around a little bit. Cool. So kind of like with our emission before, I like to layer these. So this is good. Let's make another one though. 2 forces. And I'm going to say the difference here is that this is going to be a much smaller one. So the swirl size, again, is going to be the area in space that it kind of tiles the pattern, the noise on. So if this is 1, it's going to be an area this big, and this one's going to be a smaller one. This is a much like in the volumetrics lessons when we would layer the disturbance microsolvers on top of each other so that we can control the force at different levels. So I'm going to say, let's double it right off the bat. Alrighty. Good. That's good for now. In fact, that might even be too much already. So let's go back to 1. Great. So that's a lot of particles. And as I started to say before, it's getting kind of hard to see in the viewport what's going on because there's so many particles. Ultimately, we're going to actually want to render many more particles than this. But a lot of the look of the sim is going to be dependent on how large they are in the render, what color they are, things of that nature. So without further ado, let's move on to some preliminary rendering things. Okay. So I got some points, and we'll just try rendering some of this and see what it looks like. So come over here. Let's make a mantra raw, because that's what we're gonna actually use for our rendering. And we'll just leave it like that for now. Well, do render frame range. We can come back and change some of these settings later, but this is fine for now. Let's also go to the material panel here. If you don't have one, just make it, through here, material palette. I want to grab a constant material. It's in here somewhere. I think it's under utilities. There it is. Drag it in, and we can, it's kind of weird, like we're not seeing it when you click on it. It's not showing up here. So just come out here, go to shop. That's actually where it lives, or actually it lives in matte now, I should say. There it is, material area. So constant, so I'll call it constant particles. Good enough. And with that named, let's apply it here. We can just drag it in onto it, or you can just find it in here. Either way, it's fine. And that should be enough to go to our render view. And there's the ROP that we made, the actual mantra renderer, and say render it. There we go. And that's it. So I hope you enjoyed this lesson, and I'll see you next time for Particles 2. And jokes. Anyway, so yeah, obviously this doesn't look very good. We can see it. I mean, it renders quickly. Certainly it's got that going for it. But, this isn't really telling us much of anything. First of all, they're too big. So let's make them smaller. All right, so let's actually start to render this thing now and adjust the size and color and stuff like that. So let's go over to the out area here, drop in a mantra node, and we'll deal with some of the settings later, but for now, just leave that there. It's good enough. And that's honestly all we need. We can just go to render view right now and say click render, and that's what we have. And looking good. Pretty much perfect. And that's it. That's what good effects looks like, and that's what you came here for. Maybe we can make it a little better though. So let's go into here and let's do a point Vaught. One of the main things we're going to want to tackle is the size. The size is handled through an attribute called p-scale. Now, unlike before, when we were setting the color and the velocity on this thing, p-scale doesn't exist here, but that's okay. We just need to make a bind export, type p-scale here, and now we can set this by inputting something into it, just like as if we were inputting into this. So for example, we could drop a parameter down and say something like, we'll call overall skull, or maybe even overall scale, and like that. And now I can say a whole lot of nothing, because we didn't actually look it up. Look at that. So there you go. So now we can change it. Obviously it renders pretty fast because there's not that many of them. So we can just tweak that till the cows come home, but I'm going to start at 0.02. There's a lot wrong with this. There's a lot that doesn't look particularly good. The first thing I would say is let's leverage the fact that we know the age and we know the life of each of these things. Meaning we know how long again it's been alive and how long it's allowed to live. And we can, from that, we can divide the age by the life to get a value from 0 to 1. Come on. There we go. age by the life. And so now we more or less have a value from 0 to 1. It can actually go over 1 here because of the inaccuracy. Like it might actually have an age that's a little bit over its life. So just to be safe, let's clamp it from 0 to 1. And with that number, I'm going to say multiply that number by our overall scale here. And that can be our output. So what is that doing? Well, it looks different, at least. What's happening here is that these particles are getting bigger as they live. As longer they're alive, the bigger they get. Now, that's not what we want. We want the opposite of that. We want them to get smaller. Essentially, we want them to fade out as they get bigger. All right. Well, we could reverse it. We could literally take the complement, which is an operator that all it does is a 1 minus the number. And you'll see now, they start big, and as we move out, they get smaller and smaller. So that's good. We want that. Now, what else, though? What else is going to be the mantra for this entire lesson? What else would be, how about the particles themselves have a more interesting distribution of, maybe they shouldn't all, like they should all fade out, but they shouldn't always all be the same size. Or they shouldn't all start the same size, as I was about to say. So to do that, let's just start them at a random baseline size. Now this random number will return a float, a scalar value between 0 and 1. So that sounds nice. And you have to base it off of something. We could base it off of their point number, except that their point numbers are always changing as more points are being added and deleted. The ID, however, does not change. The IDs are never reused. Even after a particle with an ID dies, when new particles are spawned later, the ID is retired. So here we go. So I'm going to say, instead of doing this thing based on life, let's just hook this in here for a minute. And we can see, well, sure enough, we have a distribution now of different sizes. Another problem, though, is that this is a uniform distribution. We have just as many small ones as we have large ones. We never want that, or we pretty much usually never want that. I would say typically we want to have a few large ones and many small ones. The way we can achieve that is by using this power. We want to raise this to a power of 2 or 3. So if I go to 2 here, you can see we still have the ones that were big are still pretty much the same size. But the ones that are smaller or mid-range got smaller. So if I do 3, it kind of suppresses it even more. So now we have some big ones and many small ones. In fact, we probably have a lot now that are just so small we can't even see. So let's bring some of them back. I'm just going to add 0.5 to everybody. That way nobody ever actually gets to 0. Great. So now we have a distribution of some big ones and many small ones. And instead of making that the only thing, let's combine that with the overall scale and with the fact that it gets smaller as it moves away. Cool. So that's something. Something I want to get rid of, though, is these colors. We don't actually want this to be white and gray. I have a much more energy looking cool thing in mind. So I'm going to say, save it. In fact, I'm going to pause this for a moment. Let's come back out here. So let's choose a frame where we've got more particles like this. Let us say that we want this to have a color based on how long it's been alive. Like it should fade out in color, or maybe even across colors over time. We can do that. In fact, we just established that we have here a number essentially between 0 and 1 of how long it's been alive. So I'm going to feed that number into a ramp. Ramps are pretty cool. So this ramp parameter will take a 0 to 1, 0 meaning use the color on the left side of the ramp, and the 1 being use the color on the right side of the ramp, and we can put as many colors in between as we like. So I'm just going to say that Oopsies, there we go. That will be that. So you can see they get whiter over time now. See that? How they all start, pretty much all start dark. And they get brighter over time. That parameter actually lives up on top with the rest of the parameters. So let's name it something like color ramp. And we can have it even say that in case we forget what that is. And I'm going to say, let's have it mostly be this kind of teal, turquoise-ish, tealish look like that. And let's have it actually start bright white. So it starts with like a piercing magnesium white, and then when it's finally about to die, it can be this kind of dim blue. So this is going to be our range until we change it. And you can see it looks like that. You can see it becomes blue as it goes on. These ones towards the edges. Oops. Like that. And again, it's hard to see in the viewport. So this is especially important now to look at it in here. So we can see that it certainly all starts white, becomes like that. Okay, so these particles are obviously still too huge. So I'm going to say, reduce this by 1/10. So now the particles are pretty small. But now we can realize that we probably don't have enough particles. So let's go to our simulation. And let's make sure that we're working with, like, this is 100,000. Let's up that by a factor of 10. So now we're going to be putting 1 million particles in here every second. But that's okay. We can still handle that. So something like that. So that's not bad. We got lots of little particles. You can still see it. It renders pretty fast, hopefully on your computer as well. Good. We can kind of see the shape. It's definitely fading out and getting smaller as it goes. I want to actually make another ramp. Let's have it, for example, I don't think that the particles should start full size necessarily. Not that these are that big, but I think it's a good idea to use the other kind of ramp here. We'll call this size ramp, where we can actually say, instead of doing color, do a spline. And this spline here, we can draw it like this. So once again, we're going to say, well, I guess I should hook it up. I keep forgetting to do that. We can say, how about ramp in and then maybe quickly ramp out again too. So I'm going to add this into our multiply also. So now it's smaller than ever. But the point is, the particles will start small or basically non-existent, quickly become large, and maybe they should still be white when they're that large, and then fade out like that. Something like that. Cool. So I'm gonna don't need to simmer right now. Okay. So that's cool. What else? Alrighty. So let's see. Let's move this further along into the simulation. I'm going to say by frame 48, we know that even the oldest particles will have to be dying now, because we said that they would start with a life of 1, and we varied it from 1 to 0. So once this comes back to us, all right. So there we go. So this is a pretty full array of everything. So now we can get a better idea. For example, I'm not seeing any of my dying particles that should be blue in here. And that's probably because they're so small that they might as well be dead at that point. So I'm going to say, let's move this up. Hopefully see more of that. Also, the particles might be actually too small. Let's give this 50% more on that. If they start to see them coming back. somewhat. I'm going to say also probably this should go fully up to 1 so that this is never reducing the size of anything. Now it'll go from 1 to 2. Remember that this is returning something from 0 to 1. This is remapping it to a different 0 to 1. And now by adding 1, it's going from 1 to 2. So that's not bad. So I want to like kind of sanity check this to make sure that we ever see blue in here. So now I can start to see some blue in there. I could probably move this up. What is that? Get out of here. All right, now we can definitely see some blue. Then I'm going to say, so that's looking pretty cool. I'm finally starting to be a little happy with this. Something I would say is, in order to make this look like a bright popping energy look, I'm going to say going into the color here, let's just multiply it by like 2 or something. We could make a parameter for this, but this is fine too. So now it's just got this like brighter look. These numbers are literally like over, let's say 1, 1, 1 for white. These might be like 2, 2, 2 now. But you can feel it. You can feel how it has a brighter, like a pop to it. Great. All right. So we're really getting there now. What else do we want to do? Okay, so before we kick off a test render, maybe this could be a little bit nicer of a color. Or maybe it should be like this cool purple here. Yeah, that's cool. Now we can kind of see it. I like that. All right, so something like that. And, you know, obviously entirely up to you. I would also say, though, overall, one of the most important things that we might want to do now is we've got 1 million particles coming in. I mean, we can go way higher. I mean, you saw how fast it was to simulate this, even as we were playing around with this stuff. I would say let's do one of my favorite old things here, and that is let's make a take where we make an HQ mode. So I'm going to say normally we're in this mode here. We can change everything. HQ, once we make a take, we can't change anything unless we specifically ask for permission to do it. And then it just allows us to make overrides and store them in these takes that we can change around. In this case, I'm going to say it's nice just bringing in 1 million particles a second to work around interactively like this. But I think when I actually render, we could probably get away with a lot more. So I'm going to say in HQ mode, let's bring this in and do 4 million instead. That's 4 million. So as you can see, in main mode, back to 1 million. In HQ mode, 4 million. Awesome. So that's cool. And if we're going to have 4 times as many particles, then we're probably going to want to bring the size down. You figure as the radius is halved, you can fit 4 times as many things in there. So I'm going to say right here, size and color. When we're in HQ mode, I'm going to, because we just added 4 times as many particles, the existing particles should be half the size. So 125 would be half the size here. And there we go. I don't have this thing on, right? Good. Let's just stop it there. Awesome. Very good. So this is enough, I'd say, at this point to say, let's get a test going just to see where we are. So let's go back over to the mantra node, make sure that it is doing the frame range. I think it would be useful to turn on motion blur. Motion blur we'll get because we have the velocity on here, so it'll streak them a little bit. And if we're doing motion blur, I like to do shutter offset -1 for this kind of stuff. There we go. Computer froze. -1 just simply means, as you can see here, that it's going to blur going backwards rather than looking forward. I find that the initial spawning frames can look weird otherwise. Anyway, so once we are ready, just switch over into HQ mode, save it for good luck, and just go into Mantra 1 sequence here. You can render it straight to disk if you want. I'm just going to have it do it here in my window, and then I'll come back and look at it later. Cool. All right, so I canceled the render a few minutes in just to see where we are. So it's definitely coming along. We can see lots of cool stuff and some things that could be improved probably. So for example, cool stuff is the particle sizes I think are pretty much perfect. We definitely can kind of get a sense of the pig head, although I think we can accentuate that with another effect that we'll talk about in a minute. But anyway, one thing that I would like to see more is we've got these, the jaggeds are great, but I'd like to see them get moved by the simulation force that takes over. I'd like to see that happen sooner, so we'll probably just increase the force on those pop forces. In fact, let's just do that now, and then we can continue talking about that. So in the pop nets here, go back into their main mode. Let's just quadruple it. I'll run a quick sim here to make sure it doesn't nothing crazy here. So that's good. I mean, we see a lot of these particles out here, but remember that a lot of these particles will actually be very small or almost non-existent to see in the render itself. So they're still here, fully represented here, but you don't actually end up really seeing them. So that's cool. Another thing is that there is no motion blur on here, even though I turned it on, and that must be because it's not on here. Geometry velocity blur has to be turned on in order for it to read that V attribute. So that's good. What else do we need? I think it's nice, like we just barely start to see the purplish blue at the end. I don't really think I have any issue there. One thing that I would like to do actually is have the camera spin around this. So I'm gonna say, let's make a null, and the null is right at the origin already where this effect is already centered. So I'm gonna connect our camera to it, because the camera already has its own transform here, but the null doesn't really. So because this is now parented to that, I can spin the null, and if we're in the camera when I spin it, we are spinning around this now, which I think will be a cool way to get a full sense of the pig head. So I'm just going to say whatever the time is times 3. That way, by the time we get to frame 120, we'll have done a full 360 degrees. So as you can see, we're spinning around it, and I think honestly that is enough. So let's close this guy, and let's run it again. Alrighty, so I stopped it again before it finished. The primary reason being that, I put on the null here, time times 3, this should have been fractional frame really, times 3 to actually be what I intended, which was that on frame 120, it would be times 3, which is 360, as opposed to t, which is time in seconds, which then is only like 4 seconds by the time it gets here. So you get the idea. So now we're actually rotating it around it. Whoops. So I'm not going to re-render the frame for that yet, but we do get to see other stuff. We can see, for example, how much more curly, noisy stuff we're getting now, which I like to see. And that's because we turn the amplitude up on those things. And we can also see our motion blur now. See these little streaks? All the little streak things there go away. And yeah, so that looks pretty cool. Even though it's not rotating around it. Oops. But that's fine. So let's make another secondary effect that's not exactly particles related, but we'll blow through it pretty fast. We're gonna take the wireframe of the pig head and turn that into like a secondary thing. Cool. So I thought we'd do one more little thing here to add a bit of pizzazz to it. It's not strictly speaking particles, but I think it'll look cool anyway. And that is, oh, not lines. That's going to be kind of like a little wireframe effect that comes in and out of the pig head here. So I'm going to say, let's merge in the, let's go out here. Actually, let's turn the particles off because we're going to render stuff in a minute. Let's grab the emitter and merge that into over here. So I'll say get emitter. And I figure what we can do here is we'll say convert line, like so. And it basically, it turns into a wireframe. It turns it into a bunch of primitives. So it's not that we're in wireframe mode, like you press W here. It's turning it into wires, like so. Something like that. So we've got that. And if I were to just say render that right now, we could start from there and just see what we get. The Mantra renderer will automatically, when it sees polylines like this, it'll automatically try to render them as strips. So one thing I'm immediately reminded of is we're gonna need a material for this. So let's copy this, and we'll call it lines. And let us, apply that to here, like so. And we can make it come into here. So much like the P scale determined the particle size from before, we can determine the width to tell Mantra how wide to make these strips. So I'm gonna say export, bind export, width, like so. And also like so, we're gonna say something like overall, and that will allow us to do that. So overall width, and we'll hook it in. It's gonna disappear again because it's gonna be getting a value of 0 now. But we'll bring it back. So something like that. So now we have thin little strips. Maybe that's too thin. Something like that. So now we're kind of getting the wireframe element of it. But right now it's rendering everything, it's rendering the black as black also. So one thing I would like to do is say, let's affect the alpha of this to actually make it disappear in certain areas. Now we already have this white to black color in here. So we want to extract that from where it's white and where it's black from there. So we'll say vector to float so that we can take the color and really just take any one of these values. And we'll say, well, where it's black, that's where it's going to be 0. The alpha is going to be 0. So we're going to need another one of these bind exports and say, this is going to write to capital alpha. And we'll say, this, let's clamp it, or rather, let's fit it. Let's do a fit to range. So we're probably going to have to modify this a little bit. So we know that some of these values are less than 0, and we don't want to set alpha to that. We want to clamp it from 0 to 1, and that's what this is going to do. And it'll also allow us to fudge with it a little bit more. So there we go. So now it is translucent, or it's transparent, I should say, in the areas where it was originally black. So that right there, we're pretty good. It would also be nice to say, maybe in the areas where it's more gray, we could make the lines thinner. So all we need to do is multiply the width times that value, like so. So now they get thinner as they approach being, black nothingness. Now these lines, as it stands, I'm going to pause this out here. Even looking at it here, there's nothing in between them. It would be nice to maybe even wave the lines up a little bit. I mean, I might be going overboard now, but we can do it, so why not? So I'm going to take a resample and say, let's give it more segments in between. So I'm going to give it 4 segments, like so. I'm going to make a point jitter, which is going to explode it. Bring it back to 0. Let's just slowly bring this up. Actually, it looks like it's maybe breaking apart. We'll need to use a fuse first here. There we go. So just to give it a little bit of staticky look to it, because again, this is an energy thing, so I figure it's nice, it's cool to like have it be like, bzzz, you know. We'll give it a seed, like we'll use FF again. So this way it looks different every frame. Like so. Let's see what that looks like in the renderer here. And I should actually go to here. Hard to see, but we can still say that it's a little more jagged now. We can bring in more of this by going in here, because remember, this area, these black areas are negative. So by coming in here, we can actually say like, remap some of that negative stuff to be more positive. So now this is being remapped to 0. So 1 is remapped to 1, negative 0.25 is mapped to 0. So the more we go down here, the more we're actually like resurrecting some of that old stuff. Oopsies. There we go. Why is that expression? Okay, so alternatively, you can go up and say like 0.5 or something. Like the higher we go, the less and less there will be. So this can be, you know, whatever you want. I'm just gonna say that. Let's see what that looks like. And I'm gonna say that this can probably stand to be twice as bright. So just gonna multiply that by 2 like that. This may end up being too much, I don't know. But as it spins, you know, it'll just kind of add some form into it, I think. And again, this will only be lit up wherever the particles are being emitted from anyway. So it'll just kind of, I'm hoping it'll just kind of taper off from where the particles are. So we'll see about that. And I should also double check that this is even going to do the right thing. So we're trying to remap negative color values back up into positive color values. So let's see, where are we? Get rid of that, CD. And we do have negative color values. Okay, good. Wonderful. So that's should be it for the line thing. Not much to do there. Just kind of a cool little extra thing. Maybe you like it, maybe you won't. Line sizes. Actually, we need to do the line color also, much like how we did before with our particle colors. So let's just grab, we'll just look at it anyway. And I'm going to say, let's make another one of these things where we, oops. And we can just copy and paste it from here, where we grab this. And actually, we don't even need to do that. We can just use this. Let's just make a ramp and say we already have our 0 to 1 from this thing. Plug it in. We'll call it color ramp. And let's just try to emulate the colors that we're already doing for the particles. So I'm going to say CD for this. Right now it's still black to white, so it looks largely the same. But once I say this should be white, and this should be this turquoise thing, and then this should be that purple thing. Let's just see what that looks like. So now it has more of that effect to it. Let's say I kind of want to bring up the white more. Something like that. Yeah, I don't even know if we really want to see too much of this purple, if any, because we're only going to see this when the particles are first being emitted anyway. They don't turn purple until much later, but I'm going to keep it on anyway. So there we go. So something like that. Great. So let us render this. Let's do one more test render on this before we call it, until we do our final render and see what we get. And now we're actually going to rotate around it. Oh, make sure we turn our particles back on. In fact, to make sure this is always working correctly, go over to our out, go to the mantra node. We usually do this first, really. Put these in the force objects and turn off candidate objects. Candidate objects means render anything that happens to be on. Now this is saying don't render anything, but do force these on. So it ends up meaning just render these two. So it won't matter if I have this on or off by accident. All right, and make sure that we go to HQ first and then render away. So that render's all done, and this is what we got. Cool, cool, cool. So it's definitely plays nicely having that underlying structure there so we can really kind of get that sense of the pig head thing, and more importantly, the particles look great. I really like all those little spurts here and there. It's, there's no like even surface here, like, of that solid wave from before. Colors look good. The distribution of the particles is nice. It's all looking pretty good. One thing I would say that if we do always intend on doing a full 120 frames, see how we have this in the beginning here? It's pretty rare that in an effect that we would probably just start emitting particles from nothing like this. Typically, you have an area of pre-roll where we would basically say, if the actual sim in the shot, let's say, is from frame 1 to 120, we would actually want it to probably start some amount of frames earlier. So for example, maybe it's by here, frame 24, it looks like all of our particles are out and about. So I'm going to say, given that let's start our scene 24 frames earlier. In fact, you can go into negative numbers here. No problem at all. So you can see, look at that. Negative numbers, crazy. And so basically we just need to say, we'll update our solver here to say start on frame negative 24 instead. And everything else should just click into place. We've made sure that all of our parameters and things that reference time, like this, are automatically gonna be correct, as you can see here. Yeah, so by the time we get to frame 24, or rather, by the time we get to frame 1, it'll be fully, in the throes of the simulation, as you can see now. So now we're all already there. And then let's make sure that we're only rendering from that frame also. As you can see here, it's saying negative 24. So let's make sure that we still start at frame 1. Yep, that's a tilde. There we go, frame 1. So we're still going to render the same frame range, and that's cool. Great. So what else do we want to do? Not much more, just some finishing touches. I would say let's throw in a ground plane. Let's have this shed some light on the ground. Like this already looks cool, but if we have like a ground to be illuminated by that, it'll make it feel even cooler. So I'm going to say ground. We'll rotate it like that. It's got to be below it, obviously. So I'll just put it something like here. Oopsies. Doesn't really matter how big it is. I'd say this is fine. We're only going to see the illumination right around here towards the bottom. By the time it gets out there, it'll be too dark to see anyway. And speaking of light, we're going to actually want this to cast light. So I'm going to say take the particles and click geometry light, like so. So the geometry light now is it looks at that thing there. We should make sure that it's looking at the output of that. I mean, it already is. It's just looking at, by just saying particles, by pointing at this, it's just going to point out wherever this is. But just in case we move this thing to here or whatever, now we can make sure that our geometry light is looking at the absolute end result. Cool. Nothing really else to do there. I'm going to say let's take a look now. Let's go back to that frame where we had everything. let's see what that looks like in terms of the ground plane. We can see a little bit of light down there, I believe. Or no, actually I don't see anything at all. And that would be because this, actually let's make sure that this is not rendering good. This is only pointing to particles and lines. So let's make sure that it also is looking at ground, like so. And I'm gonna say, let's do a regular render. I've been doing a lot of quick render stuff in that render view there, but let's do a regular render this time because it will get a higher resolution image here. So now we can see we've got this kind of glowing on the ground, and you can already feel how much nicer this is sitting in our scene, which is pretty cool. So now you can really feel like it's present there. So that's nice. It's still grainy down here. I'm not going to get too much into render settings this lesson, but I'll just say in general that I'm going to turn off, well, I'll go back to the first frame. In general, let's say under the HQ mode, we've been talking a lot about simulation high quality stuff, but we can also do here under rendering and where are you? Sampling. Let's increase this to at least 6 by 6. And you'll find that increasing these pixel samples will increase the sampling of everything, really. All of the, like, all these little dots here from the motion blur will clear up. The ground graininess will clear up here. All those little grainy things, everything was just going to look better, but of course it's going to go significantly slower. In fact, when it was 3 by 3, we were doing 3 by 3 samples per pixel, which is 9. If I go to 6 by 6, now it's 36 samples per pixel. So by increasing it by a factor of 2, we actually end up with a factor of 4, because it's squared, more work. So don't go crazy on this, but that should be still pretty doable. And a couple of things before we render. One is that, as opposed to a lot of previous Applied Houdini lessons and whatnot, I am not caching these particles, meaning I'm not saving them to disk. You certainly can if you want. Right after our solver's output is dumped here, and maybe even after the size and color is changed, we can put this in here, set a file name for it, and then save it to disk. And then load those resulting files from disk once they actually exist. And you'll basically just have on-disk representations of every single frame. Now, for us, I would say this sims pretty fast already. And we've made so many changes to the simulation that I didn't want to have to worry about caching, recaching, and recaching. Now that we're pretty happy with the sim, it might be a pretty good idea to cache this, but I'm not going to. I don't have a render farm to send these caches to in parallel anyway, so not going to worry about that. The other thing we want to do is over here on our mantra node, let's save the images somewhere and give them a better name than this. So just go over to here, you can click that guy. I like to put him in my project folder, which is job/render, and then just call it something cool like particles dot, we'll call it version 0. $F rather is the current frame that we're rendering, and .exr is the cool file format that we all love. You can see if I middle click on this, it resolves it to where it's going on my computer, complete with the frame number. And that's about it. Just make sure that remember if you're doing an HQ render, just set the HQ here on the node. You can keep it at current and switch to HQ and then do it, but that's more of a pain. So just set this to main here, HQ here, and make sure that we have cool sampling on here. If you're feeling really lucky, maybe put it up to 9 and 9, but I think 6 and 6 will be fine for our purposes for this lesson. And without further ado, that's basically it. So I'm just gonna say render, and we'll look at this in a couple of hours, and hopefully it is worth seeing. I think it will be. You can see the pre-roll countdown here, And once it actually gets to frame 1, it'll actually start to render. But until then it has to run the 24 frames. Anyway, let's do and check back on it later. And there it is, all done. So that took, as you can see, it took a couple of minutes per frame, not even fully a couple of minutes. And the extra samples certainly helped. We got the nice smooth lighting on the ground, really makes it feel like this thing is glowing and like it's in space. The samples helped with the motion blur lines, with the lines inside of the ears, and anyway, I think the particles look cool. What do you think? I don't know. I hope you liked it. And check out the other Applied Houdini lessons. The rigids that are all done. The volumes are all done. And now check out the new particle lessons coming soon as well. And don't forget to send me your stuff. I always love to see it. All right. Thanks for watching. Bye-bye.